Hello. Today we're going to begin our discussion around similarity and tie it to the dilation work that we've been doing recently. So our objective today is students will be able to define the sequence of transformations that determine similarity or define instances when similarity is not existent. Some of the words that you'll hear repeatedly today are similar, dilation, sequence of transformations, reflection, rotation, translation, ratio, and proportion. Okay, so the goal is to show that if triangle ABC is similar to triangle A prime, B prime, C prime, then triangle A prime, B prime, C prime is similar to triangle A, B, and C. And so as we begin to think about our properties, this is an example of the symmetric property. And essentially what the symmetric property does is it allows us to write in different orders the same expression or phrase or equation. So in other words, that x equals 3 is the same thing as saying 3 equals x. In this scenario, we're saying that it doesn't matter if I know that triangle ABC is similar to triangle A prime, B prime, C prime, or if I say that triangle A prime, B prime, C prime is similar to triangle ABC. And so what we need to do to even start this is prove whether they're similar or not. And so first determine whether or not triangle ABC is in fact similar to triangle A prime, B prime, C prime. And one of the original ways we started looking at similarity, or really dilation, is by ratio. So I'm going to look at A prime, B prime over AB. I'm going to look at A prime, C prime over AC. And I'm going to look at B prime, C prime over BC. And see if each one of them, are they equal? Okay, so this is really a question mark. Are they equal? Because if they're not, then I don't have similarity. The other thing you want to be very careful of, don't get into the trap of just checking one of them, because it's potential that you pick the one that is the same ratio, but the third one may not be. So in this case, I look at the ratio and I see 2 over 4. I see 4 over 8. I see 3 over 6. And in fact, each one of these is equal to the ratio of 1/2. The other way I want you guys to begin viewing these is as a ratio. So this isn't fracture form, this is the colon form. So 2 over 4, 4 over 8, and 3 over 6. And I promise you this notation will be on your exam, and so you want to be familiar with it. So I take and I put the lead number as the numerator, and so this is a ratio of 1 to 2. Okay, so that does provide us the information that we need. If you're watching the videos, this would be the side-side-side similarity. But we also know that we could have angle-angle similarity. So if I were to look back up here, we know about this angle theorem, and really it was angle theorem from the last unit. And what that does is it provides us the idea of similarity for triangles. Okay, so for triangles, and you might be wondering why I only need 2 angles. So I measured these ahead of time, but I'll just show you. You'd put your protractor on, you'd pull this out. This one measured 99 degrees, this one measured 32 degrees. And because of the triangle theorem, triangle sum theorem, we know that all the angles within a triangle are supposed to add up to 180 degrees. Well, if I have 2 of them, and I know they're supposed to add up to 180 degrees, I can calculate the third. And so ultimately, it's just a time saver. And so then I measured the other group, 49, 99, and 32 degrees. And since all 3 angles, all 3 corresponding angles are equal, sides are in proportion, I do know that we have similarity. So we know similarity based on angle. And that becomes important to understand. Okay? Turning the page over, there are 3 questions that they want us to answer pertaining to dilation. It says, describe the sequence of a dilation followed by a congruence that proves one is similar to the other. And so congruence, what they really mean is that is there a reflection, a rotation, or a translation that would map one onto the other. And sequence means more than one transformation. Okay, so I have more than one transformation. And so if I kind of look at that image once again, I do notice that I couldn't just shift this directly over. What I could do is dilate through the origin. All right, so if I dilate through the origin, I get 3 new parts. So instead of -8, 4, I'll have -4, 2. Instead of -6, -2, I'll have -3, -1. And instead of -4, 6, I should have -2, 3. Okay, and then, like I said, there's sort of clear indication that I couldn't just translate this shape over. All right, I can't just take this tinier triangle and just shift it over here, because it would kind of have the wrong, not orientation because of the way this goes counterclockwise and this goes counterclockwise from A to B, but things don't match up. Okay, so that indicates to me that I do have a rotation. The rotation is where the corresponding lines, perpendicular bisectors, all intersect, which is at the point 1/2, 4. And so if I was going to use function notation, I actually have to work from what I did last. So a rotation of about 0.4 of 180 degrees with a dilation of 1/2. I already calculated my scale factor about the origin of triangle A, B, C will equal triangle A prime, B prime, C prime. Second part says, describe the sequence of dilation followed by a congruence that proves that the triangle A prime, B prime, C prime is similar to triangle ABC. Well, we have already done most of the work here. But if I'm going to go from A prime, B prime, C prime to A, B, C, the sequence could be a little bit different. And so the dilation about the origin would happen second. So I'm going to list it out. The rotation about 1/2 and 4 of 180 degrees is what's going to take triangle A prime, B prime, C prime back to triangle A, B, C. Now, again, this doesn't have to be the only way that this happens, and in fact, you might want to think about how I could have done this in a different order. Technically, this is asking for a dilation first, and so if I were doing this, I could dilate about the origin, And what that would do to my image, it would push it all the way out. I'd push it out here, and then I'd have to rotate properly to get it to lay on top of there. Okay? So my dilation of, this should be 2. Origin 2 to triangle A prime, B prime, C prime. And then I'd have to rotate it. Okay, about that point. And finally it says, is it true that triangle ABC is similar to triangle A prime, B prime, C prime, and triangle A prime, B prime, C prime is similar to triangle ABC? Why do you think this is so? In both cases, so yes, in both cases, there exists a sequence of transformations that maps one triangle onto the other. And so that's how we get a similarity. And so we need to understand that similarity is indicated by all these acts. And so then really it becomes time to practice this. And so as you're looking at this, would a dilation alone be enough to show that similarity is symmetric? This is a great question. Okay, so can I go back and forth based on just dilation alone? That is, would a dilation alone prove that the two triangles are similar? And we consider the two examples below. And says, given this dilation is enough to show that triangle ABC is similar. Explain. And in this case, for this case, there is a ray emanating from O to each vertice connecting the pre-image and image. And really what we're highlighting is the definition of dilation. And so we would know back and forth, if you were to measure, the ratio would exist, the angles would be the same. We have parallel lines cut by a transversal, therefore corresponding angles are the same, and we're fine. But you look at this second example, and you can see that, well, A goes to B, but in this case, A goes to B in the clockwise rotation. This goes in the counterclockwise rotation, and that indicates to me that there must have been some sort of reflection. All right, so if I were to write this out, I would say there does not exist a single center point that we can dilate from. since the orientation reverses from pre-image to image. In other words, if I were to write out the sequence of transformations, I would find that I would need a dilation composed with a reflection about a line. Okay, so in this case, dilation is not enough. So dilation alone is not enough. And so in general, is dilation enough to prove? There are cases when dilation is enough to prove similarity. But in general, which is what they asked, dilation is not enough to prove similarity. It would ignore reflections and rotations. Okay, so a big takeaway from this is that when I want to prove similarity, if I'm going through an actual proof, frequently I'll have to use rotations and reflections in conjunction with a dilation. Okay, now remember the objective was to be able to prove or disprove. And so when I'm looking at this next picture, I can see that I have all sorts of parallel lines cut by transversals, and allows me to know angles are the same. I can count the boxes between, so this has an up and over of 1 over 2, up and over of 1 over 2, up and over 1 over 2. And so I can see how the distance is maintained for each one. So we could talk about the dilation from the point O and having everything stay in proportion. And so given triangle ABC is similar to triangle A prime, B prime, C prime, and triangle ABC is similar to A double prime, B double prime, C double prime, is dilation enough to show? And so you could say yes, a dilation alone is enough to show transitive property. Sides are proportional. Corresponding sides are parallel, and a center exists at 0, 0. Okay. The other thing you'd want to do is just make sure that the lengths were in proportion. And then you have a scenario like this one. Okay, so if I go from A to C to B, is a dilation alone not? All right. And we can definitely see that the orientation of the letters on the triangle, so A goes to B in a clockwise rotation, the other one, A goes to B in a counterclockwise rotation. So there's some sort of reflection that occurred, so no dilation alone is not enough to prove similarity. Because after the transformations, including dilation, I should have one mapping onto the other. Okay? So the takeaways from today, one, make sure that you know how to prove. And again, I go back to one method would be the angles. The other method is this ratio. Make sure the ratios all line up. The transitive property cannot be assumed between dilations of or similarity between shapes, because you could have a dilation with a transformation such as a reflection or a rotation. So you've got to have a sequence. So similarity is defined by the sequence of transformations. You can use the ratios again and the angles to prove similarity. Thank you for your time.